Welcome to the Light and Sporty Guy channel. I'm Jim. In this video, I'm going to try and give you a reasonably intuitive and easy to follow explanation of how a wing generates lift that's actually consistent with the laws of physics. And we'll be using a lot of computational fluid dynamics so we can do some sanity checks to extrapolate our numbers from the simulated wind tunnel thing to actual flying things and make sure that what we're doing makes sense. And I will say there is not one correct way to get from an airfoil to lift, but I believe what I'm presenting is, I think, the most intuitive way that is actually consistent with the real life physics, okay? There is a lot of mythology out there, and I will touch on some of those myths here and there as we go, but that's not the primary object of this video. And I did cover this topic before. This is a total remake of the earlier video. I've replaced a lot of the hand-drawn cartoons with images from the Computational Fluid Dynamics software. I've changed up the approach a bit to, I think, make it easier to follow, and I've tried to address some of the questions that came up in earlier videos. And of course, down below you'll see the chapters, so you can skip around and hit things of interest if you want. So to start this off, we're going to use computational fluid dynamics to analyze a thin cross-section of this airfoil on this balsa glider right here. I'll use a simulated airspeed of about 6 meters per second, which is approximately how fast it flies in my shop based on just 1/1000, 2/1000 kind of timing. Not accurate, but it gets us in a ballpark. Now, to be clear, this is not a very good airfoil, but it does let us look at the basics of lift without complications due to airfoil shape and invoking nonsense like airfoils generate lift because they're flat on the bottom and curved on the top. And I will also come back and compare a traditional airfoil just to make sure we didn't miss something and, for the sake of completeness. This is the model I created in FreeCAD for the simulation. The inlets on the left, outlets on the right. The airfoil is that orange shape, and the simulation of space is bounded by the other sides that you see. I kept it narrow to keep the time needed to simulate this to a minimum on my laptop. And for what it's worth, I will put a link in the model in the description if you want to play with it and try to either confirm or refute my results yourself. And this is the result. We see a lower pressure, which is more blue over the airfoil, and a higher pressure, which is more red under the airfoil. And we can see that the effects extend all the way up to the top and down to the bottom of our simulation space. The strongest effect is right here at the leading edge. Now, to pick one little nit, by definition, lift is up, or 90 degrees to the direction of the airflow, while pressure is, again, by definition, 90 degrees to the surface. So lift is not exactly equal to pressure difference, but it's still fundamentally a function of the pressure difference, since pressure is the primary force acting on an airfoil. Now, in this case, some of the pressure difference goes into drag along with the surface friction, with the pressure and viscous surface friction being the only two forces that are applied to an object in a fluid such as air. Okay? And the CFD, Computational Fluid Dynamics software, lets us get the sum of the forces in the up direction, which is the lift. And just for a sanity check, the model itself weighed 10 grams, and if we assume that the coefficient of lift was 0.326 for the entire span, we get a lift of 11.2 grams, which is a little bit more, but that's ignoring the fact that lift falls off near the tips, so we probably are a little short on the total lift needed, and to get the exact correct lift for a three-dimensional model, we'd have to fly it a little faster, I think. But still, may not seem like a big deal to you, but for somebody like me who's not a CFD guy and just screwing around on my laptop, this just blew my mind that we came this close. Now let's look at the streamlines, okay? We can see some curvature, particularly near the leading edge, and we see a net downwards flow as we get to the trailing edge. But let me squeeze the image from side to side to better show that curvature. What do we see? Well, we see that the flow is actually affected over most of the simulation space. You know, these are the lower and upper boundaries where it can't curve, but the airfoil affects the air for a pretty significant distance around the foil, in front of it, behind it, and we see the upwash here curving over the leading edge, downwash there. So what does all this mean? Let's quickly review Newton's second law so we understand the relationship between flow curvature, like we see over here on the right, and differences in pressure. Okay. Assume we have a virtual cube of air, ignoring viscosity for the moment. The force on any face is the pressure on that face times the area on that face. And the net force on our cube, as it's drawn, is the difference in forces on the right and on the left. So pressure difference, as shown with the bigger on the left, will accelerate the cube to the right. And we also know that the mass inside that cube is the volume of the cube times the density. And the net result is that the acceleration of our cube is essentially the pressure difference between the right and the left divided by the density, since the areas all cancel out when you do the math. Now, if we have a cube that's already moving left to right, like air flowing past an airfoil that is in motion, the pressure difference between the top and the bottom will cause the flow to curve as shown, matching the curvature that we see over and under our airfoil. So if the pressure some distance above the foil is near the ambient pressure, then according to Newton, the pressure on the top of the airfoil is lower here to cause that pressure difference, which causes the flow to curve, okay? And on the bottom, the pressure here near the airfoil has to be higher than the pressure down here where it's near ambient, again, to cause that flow curvature. So overall, Newton is telling us that the flow curvature and observed pressures go hand in hand. You just can't have one without the other. And here's a screenshot from a video of a wind tunnel test done by NACA in the 1930s. And we can use this for a little bit of a sanity check. If I squish this one, you can see the flow curvature a lot better, and it's in general pretty similar to what we saw on our previous slide. Now, are Newton's laws enough to explain all of the lift, or is there some mysterious Bernoullian component that we haven't touched on yet? Well, if the air is lifting the airfoil up, Newton's law says that the air has to be pushed down, so in turn, the air should push on the tops and bottoms of our simulation space with a force equal to the lift. So, are Newton's laws really enough to explain everything that's going on? Does the force up on our airfoil match the force downward on our simulation space? Well, our force up is 0.001798 newtons. Not very big, but it's just a little slice. Our force down, minus 0.01734, which is close, but yeah, no cigar, I'm sorry. 3.7% is getting big enough to make me wonder if we missed something. So yeah, we got a rabbit hole to go down here. Hopefully we don't have to go too far. So what I did here is I zoomed in on the vertical velocity in the, okay? So we can really see where there's any Z direction or up and down movement, okay? And out in front here, um, where it's more redder, that's more up, more vertical. So there's a lot of vertical movement in front of the airfoil where the air is going up. And then this white line here, this is where the peak of where that flow curvature is going from up and then over to down. The bluer is downward flow. You can see the wake behind it. You can see where the peak of that curvature is down below the airfoil. And you can see that the velocity extends pretty much to the upper and lower bounds of our simulation. But what I noticed here when I looked at this is way over here on the left, there's still some upflow, and way over here on the right, there's still some downflow, suggesting that the flow effects of this simple flat airfoil extend beyond the limits of our simulation space. So let's fix that. I've doubled the length of my simulation space. Now the up force changed a little bit, less than 1%. The down force changed quite a bit, and we've gone from a 3.7% difference between the lift and the force on the wind tunnel, if you would, to less than 1%. So I'm feeling a lot better. I'm feeling like we've captured all of the effects, and it all seems very Newtonian. But of course, this is just a simulation. What about real life? Okay, so here is a real life experiment. I have a quadcopter in a box. It's all closed up. There's a scale under one end of the box measuring essentially half the weight. And it's measuring 435 grams, as you can see. And when I lift the quadcopter up by hand, the weight goes down to 375 grams. So it's about a 60-gram difference. And it's about 60 grams is about half the weight of the quadcopter, so it's working. So when we spool up the airfoils, the propellers, if there is some non-Newtonian lift going on here, something that isn't totally explained by the flow curvature and pressure gradients and equal and opposite reactions, then we should see the scale drop, to what, 420, 410, something, okay? But let's play this video and see what happens. So I'm fired up the fans and it's spinning faster and faster. I'm easing in the power. Scale's pretty much just sitting there, even though the rotors are spinning, and we have lift off, and it's bobbling around a couple grams as things bounce on the strings and things like that. But we're flying, and the weight in the box is indicating that, equal and opposite reaction. We're shoveling the air down, and the air is pushing the quadcopter up, and the air is pushing down on the bottom of the box, and that's all there is. And also, just for the sake of completeness here, let's wrap up our work with the balsa glider. This is the simulation of the velocities around the foil. Again, redder is faster, and we see red over the top here where we saw the low pressure, just like Bernoulli would predict. Blue is generally slower, so we see this bluish color here. Again, nice in line with Bernoulli. And we also see a lot of blue along the foil in the boundary layers where the air is slowed down through viscous drag on the foil, and the wake of the airfoil as well is blue. And I should note that Bernoulli's principle, which assumes that viscosity is insignificant, doesn't apply in the boundary layers because we're not conserving energy. Energy is being lost through the viscosity and drag on the surface. So the fact that the pressure is slower here, or the fact that the velocity is slower, does not mean that the pressure is higher. It just means that Bernoulli does not apply right there. But what about a real airfoil on a real airplane, okay? So let's take the airfoil from a Cessna 172 and the NACA 2412, and we'll simulate it at 172-ish speeds. I'm a little bit slow here. I picked 100 miles an hour because it was just a nice round number. And we'll set our angle of attack again at 2.6 degrees, and that's the way it's drawn here, with the bottom about as parallel to level as I can get it. Over to the right, we have the wind tunnel data from Theory of Wing Sections by Abbott and von Donhoff. They collected the data at NACA, and this vertical red line is about our 2.6 degree angle of attack, as close as I can eyeball it. And we come up to our lift curve, and we go across, and we get a lift coefficient of a bit over 0.5, so we can use that kind of number as part of our sanity checks. So I will point out between these two pictures, the pressure scales are different because the conditions that we tested them are so much different. They're just not going to fit on the same scale. But on the flat airfoil, we had, concentrated low pressure right here at the leading edge, where the air has to make that screaming turn around the leading edge. On the 172 airfoil, it's much better behaved. We have the gradual turn. We have low pressure air spread out over most of the top. We have the high pressure here underneath. High pressure under here isn't quite as pronounced as it is right there. That's just the nature of thicker airfoils, because the air has to squeeze around the top and the bottom. And the thicker you make the airfoil, the lower the pressure on the top and on the bottom becomes. But that's for another video altogether. And also, the camber in the airfoil gives us more lift at a given angle of attack. But our coefficient of lift that we calculate here of 0.55 is pretty darn close to the value from Abbott and von Donhoff, which was just a bit over 5. So I'm feeling good about my data. And we can look at our streamlines just like we did before. And I'll squish this in again so we can compare it to the flat airfoil. And again, we see the flat airfoil had the real sharp peak near the leading edge. Here we have a broader, more spread out curvature, better behaved generally, but again, it extends quite a ways above and quite a ways below the airfoil, limited by the edges of our simulation space. Okay. Again, the colors are different here, but you can see on the NACA 2412, the higher velocity is spread out more over the top, whereas on the flat airfoil, it's primarily where the air goes screaming around the corner there. We have a larger low speed area where the air kind of bumps up against the nose of the airfoil. The slower air speed underneath is not obvious, or not as obvious. Not a surprise, because as the airfoil gets thicker, the air has to squeeze around both sides and the velocity increases above and below, but that's a topic for another video. And the $64,000 question, is Newton still explain what we've got going on here? We drew the airfoil with the bottom approximately parallel with the relative wind. We calculated the up force from the airfoil at 194.29 newtons. So our calculated downforce is 194.31, which is only about 1/10 of 1% difference from our lift. So yeah, Newton, right? Pretty much explains everything that's happening, even on a real simulated airfoil like this, okay? And just one more sanity check: if we apply that lift across the entire span, again ignoring the fact that lift distribution drops off near the tips. It could lift about 1,400 kilograms compared to the 1,100 kilogram gross weight for an actual 172. To put that into pounds, it's a bit more than twice as much, bigger in numbers, but the math is left as an exercise for the viewer. And we've talked about Newton and how turning and the flow and the low pressure go hand in hand. So the only real mystery left is why the airfoil tends to follow why the airflow tends to follow the top surface of an airfoil. One word, viscosity. The viscosity of air is low, but it's not quite zero. Initially, when the airfoil starts moving, the flow isn't attached. The flow over the top just kind of goes on its merry way. But since air has viscosity, we tend to pick up the air in this space between the free flow and the foil and entrain it into the flow and drag it out of there, and it starts pulling the air out of there. It tends to reduce the pressure in this space between the airfoil and the free flow. Okay, it's not Bernoulli because we're taking energy out of the streamlines and moving it into the initially still air. Okay, but as that pressure drops there, the tendency is to lower that to curve the airfoil more, and the space between the flow and the airfoil gets smaller, and we continue to move more air out of that space until eventually we get a nice clean flow right along the surface. Okay. Of course, if the angle of attack is too high, the viscosity isn't enough to keep it stuck, and it doesn't make the turn, the corner, and then the flow separates again, and that reduces the flow curvature, which reduces the lift, and that's when you have the aerodynamic stall. Okay. So to kind of wrap things up here are some of the tools I used to do this. I did all the computational fluid dynamics in FreeCAD and the CFD OF workbench. When you install that workbench, it installs CF Mesh to do the meshing. OpenFoam does the heavy lifting for the computational fluid dynamics. ParaView is what is used to generate all the graphics that you saw. Xfoil is another tool you can find and download. I didn't use it in this presentation, but I've used it for others, and it's useful if you want to play with this sort of thing. Octave is a MATLAB compatible syntax computational tool. I use that a lot now that I no longer have access to MATLAB at work. University of Illinois at Urbana-Champaign Applied Aerodynamics Group. They have the incomplete guide to airfoil usage along with an airfoil database and a bunch of other sort of tools that you can use. And again, I will upload the models that I created. The link will be in the description if you want to open up FreeCAD and play with them yourself and see what you can do with them. Go right ahead, of course. And that is that. I hope you found this at least interesting. I do have more videos in this series that get into topics like Bernoulli's principle, circulation, the effects of airfoil shape and stuff. Some of those will be updated in the future, I think. And so I'll thank you for watching, and I'll catch you on the flip side.